This conference will now be recorded.
Hello students, very good evening to all. Today we are starting a new chapter, alternating current. Here we will be discussing in the similar pattern various questions from previous year's JEE main papers. So basically I will be collecting various questions from previous JEE papers and discussing on this chapter, alternating current. So today we have picked up few questions. Let us try to solve and discuss. So this first problem, let us try to solve. In an LCR circuit given below, as you see, it is not actually LCR. Yeah, so this L and C, they are parallel in connection, and this is series to this. Okay, basically what is given here in this circuit is, this is not our conventional LCR series circuit. It is this is L and this is C. So this is the thing given here in this problem. Okay, and this is connected through switches as you see here. So this is R, this is L, and this is C. So this C and L, they are parallel in connection, and that whole combination is in series with this R resistor. Okay, now so the question is, initially both the switches are open, S1 and S2, there are two switches. You can see here, if S1 is closed sometime and S2 is open, then this CR will be connected to battery. C and R, they will be in series, and if the C1 is open and this C2 is closed, then L and C, they will be connected, and this will be actually this circuit. Okay, that means there will be no battery connection with this uh, circuit. Okay, so here the question is, initially both were open, now S1 is closed and S2 is open. S2 is open. See, S2 is open, S1 is closed. That means, you know, the circuit is closed now like this. Okay, so current will flow through both R and C, but there is an open circuit here, so it will not flow through L. That means, see, you have a circuit now, CR circuit. Okay, you know that this is a CR circuit, and it is actually DC voltage applied to CR circuit. That means what will happen? This is actually a charging circuit or charging configuration of a capacitor. So whenever you want to charge a capacitor, you have to take one R and you can connect R and C in series like this, and with the battery, this is a DC battery. So this is kind of charging of capacitor. Okay, charging of capacitor. All right, this is kind of charging of capacitor. Now here Q is the charge on the capacitor, and tau, you can see tau is the time constant. It is written as CR. Okay, time constant. It is actually time constant. Okay, so which of the following, this is capacitive time constant, that's why it is CR. Which of the following statement is correct? Which of the following statement is correct? See, the statement number 1 is saying that work done by the battery is half of the energy dissipated in the resistor. So work done by the battery is half of the energy dissipated in the resistor. It cannot be true. Let us go to see the other options. So this option says, so here C1 is closed, sorry, C1 is, just a minute, here there might be some typing error. So switches are initially they were open, then S1, now switch S1 and S2 are both closed. Okay, both are closed. Yeah, so both are closed. Initially both were open, now both are closed. Both are closed. Then which of the following statement will be correct? Okay, so this is what we have to answer. So we can see for charging a capacitor, this is actually charging circuit as I said. So both are closed. You can see this is actually a charging of capacitor. And as you know, since this is a DC current, even though this is open, sorry, this is closed, if both are closed, see this is an inductor coil. So there will be EMF or energy stored only when current is varying current. Okay, only when current is varying or AC current. In DC circuit, actually in DC circuit, there is no function of this L. Okay, only when current is varying. Let me write. If current is varying, L will produce a back EMF, and thus actually it will store magnetic energy. We can write, since the okay, will function. Let me write this as L will function only when current is varying. Since the current is steady current, see what it does generally, it produces an EMF, back EMF, L d phi by dt. Okay, or sorry, L di by dt. So this is the kind of EMF it will produce, and from there actually it will store a magnetic energy. But since this is not varying, so this factor will be 0. So ultimately there will be no function of this. Okay, no function of this inductor coil in the DC circuit. So we don't bother about this. Don't bother about this L. Okay, so when both are open, nothing is happening. But when both are closed, when both are closed, both, let me write, both switches are closed. Are closed, then the circuit, equivalent circuit is actually a charging of capacitor. Okay, then the circuit is nothing but a circuit for charging capacitor, as I was showing in the beginning, charging the capacitor. Okay, so your equivalent circuit will be along with the battery. Okay, so along with the battery, this is a charging circuit for capacitor. So if it is charging circuit, how charge gets stored in the capacitor? So the charging equation we have to write. Charging equation for capacitor is given by Q is equal to Q0 e to the power minus T by tau. Okay, so this is charging circuit. So Q means CV, okay, and Q0 means CV here. Q is CV, okay. So we can write this C is the capacitance and V is the total voltage. So let us write this as CV. Because this is the equation while charging happens in capacitor. Now look, I'll just erase this line. So the three options, let us see. When t is equal to tau, exactly tau, then what happens? See, it will be Q is equal to CV1 minus e to the power minus 1. This will be the case. Now when t is equal to 2 tau, Q will be CV whole into 1 minus e to the power minus 2. Okay, so now look, it is not going to become C by V CV by 2 at t is equal to tau. Okay, so the correct answer will be, see, at t is equal to 2t, this is fine. At t is equal to 2t, q is this, so this is also not true, this is also not true. So this is the correct answer for this question. Okay, so correct answer is this one, C. At t is equal to 2 tau, q will be equal to CV C into V whole into 1 minus t to the power minus 2. Work done by the battery is half of the energy dissipated in the resistor. This is not actually true. Okay, all right, we'll go to the next question. So here also we can see there are two switches, and this is this is Henry means this is L and this is R. So this is a series LCR circuit. When there are two keys, one key is actually connecting the battery of 15 volt. See, even though this chapter is actually alternating current, but here see all the batteries are, so far we are seeing only the DC batteries. Okay, and here there will be very interesting problems. Okay, this is from JEE Mains 2015 paper. Let us read the problem and try to solve. So an inductor L is equal to 0.03 Henry, and a resistor 0.15 kilo ohm. So L is equal to, let us write the values. L is equal to 0.03 Henry, R is equal to 0.15 kilo ohm. So this we can write as 150 ohm. You can check it. Okay, so and this could be actually written. Okay, let it be like this. So this connection, circuit connection, is shown in the figure as you see here. Connected in series to a battery of 15 volt EMF in a circuit shown below. The K1 has been kept closed for a long time. K1 K1 is kept closed for a long time. You can see that. And then at t is equal to 0, K1 is opened. K1 is open at t is equal to 0. And K2 is closed. K2 is closed. Okay. The question is at 1 millisecond, the current in the circuit will be how much of this? Okay. How much will be the current flowing through the circuit? So I'll just repeat the question again. See, in this, there K1 was first closed, K2 was open, and this was kept closed for a long time, this K1. And then after a long time, at t is equal to 0, K1 is open and K2 is closed. Simultaneously, this is done. Simultaneously, it is done. So at t is equal to 1 millisecond, what will be the current in the circuit? See, in the previous problem also, we had seen when DC voltage is applied, nothing was happening with this. Okay. So here also, when this K1 is closed, K1 is closed. So then what is the current in the circuit? So current can be obtained I0, suppose I0 is equal to voltage, that is the battery voltage, divided by R, right? Resistance R, because this L is not going to see for a long time. When you keep the K1 closed, there will be current, steady current flowing through the circuit, and for steady current, this L will not provide any obstruction or any resistance. So the current will be actually voltage is 15 volt, and resistance 0.15 kilo ohm, means this much ohm. Okay, so you can see this is so 0.1 ampere. This is the current. So this is the current. It was there in the circuit initially. Now if K1 is open and K2 is closed, this I0, since there is no battery, and it is actually done very quickly. And see this, we have to see the current in the circuit in 1 millisecond, a fraction of second, very small interval of, like very small, after very small duration of current we have to see, sorry, time. So as soon as you open this, you close this simultaneously. So now the current will be actually decreasing. Current will be decreasing exponentially in the LR circuit. In the LR circuit, current will be exponentially decreasing in the LR circuit. Okay. So since it is done simultaneously, there will be a variation of the current in that case, actually variation of current. So what is the decay of current in LR circuit, series LR circuit? So decay equation, okay, decay of current in series LR circuit, this is actually from transient phenomena, that means instantaneous phenomena. Okay, so the decay of current will be written as I is equal to I0 e to the power minus t by tau. Here in this case, tau is actually L by R. Okay, L by R. Now let us go to the next page and do the calculation. So I is equal to I0 e to the power minus t by tau, or I0 into e to the power t by L by R. So R will be in the numerator in the exponential factor and L will be down. Okay, now we can find out. Say I know T is given as 1 millisecond 10 to the power minus 3 second. R is given as 150 ohm and L is given as 0.03 Henry. That means 3 into 10 to the power minus 2 Henry. If we put all this, see, let us first find out what is T R by L. So T is 10 to the power minus 3, R is 150, and so this is L is 3 into 10 to the power minus 2. So we can see that this will be 5. Okay, this will be 5. So this factor is becoming 5, and this obviously this has to be a dimensionless quantity. So e to the power, this is e to the power minus 5, or I0 e to the power 5, and it is given that, okay, let me just erase this part. It is given that e to the power 5 is nearly equal to 150. So we can write I is equal to I0 divided by 150. So 0.1 divided by this ampere, or 1 over 515 into 10 to the power minus 2. If we, so this will be actually 0. Sorry, this is 90, so 0, this is 1, so again this will be 0.66. So let me check with the options. So it will be 0. This 0.67 milliampere. Okay, this will be the answer. I hope you have understood this. So initially when cave was kept closed for a long time, the current, only resistance will have for this resistor coil, not for the uh, inductor coil, because it will be acting as a conducting path, okay, for DC. Okay, so that's how we could find out the maximum current in the circuit. And when you open this K1 and simultaneously close this K2, and you see the current in 1 millisecond, then the current will actually decrease exponentially to 0, and it will follow the equation I is equal to I0 e to the power minus t by tau. Okay, so from there we have solved it. Now okay, so now in this question number 3, an arc lamp requires a direct current. Arc lamp requires a direct current 10 ampere. So I is 10 ampere. This is direct current or DC current, and voltage V is 80 volt. If it is connected to a 220 RMS and 50 Hertz AC supply in series inductor needed for it. So if you want to light this lamp, how much inductor you have to put with this in series with the battery 220 volt RMS. That's the question actually. So here you look, the bulb has certain resistance. So this bulb requires this much current and this much voltage. So we can find out from here what is R. R is equal to V by I. So V is 80 and 10 ampere is the current. So this is ohm. 8 ohm is the resistance for the bulb or arc lamp. So lamp has resistance R is equal to 8 ohm. Now if, see, now what we have to do, lamp, arc lamp that has certain resistance, and you have to connect an inductor coil in series with the battery. Okay, with the battery. Battery is given here. This battery is not a DC battery. It is an AC battery. So this has V is equal to 220 volt RMS voltage and 50 hertz AC supply. Okay, so in this case you have to find out what is the value of this L. R we have already obtained for this lamp. We have to find out L. Okay, so in this case, see, we know that the current will be, or the voltage, given voltage will be actually dropped across both this. So since it is AC signal voltage, so there will be equivalent impedance for the circuit. That impedance will be given by omega into L plus R square. This is whole square. Okay, this is whole square. So you know this will be V will be given by I into Z. So what is this I? So what is this I? V is equal to IZ. Okay, so I is given already. Okay, I is already given. That is the DC current. So DC equivalent current we can find out. So let us first do one thing. Here DC equivalent uh, DC equivalent voltage, actually the total voltage will be VR plus VL. Okay, this is the total voltage. So sorry, this is V square. If you go with this phasor diagram and all, V square is equal to VR square plus VL square. So this is equal to, then this is 220 whole square. VR square will be 80 square because it is given already, and VL square, let it be like this. So from here we can write VL square is equal to 220 whole square minus 80 whole square. So this would give you, see, this VL, if you calculate, you will get something like this much. Okay, VL is equal to 205 volt you will get. And now you know this VL means XL into I. XL into I. Okay, XL means what? Omega into L into I is equal to VL, or L is equal to VL by omega into I. Okay, I is the current in the circuit. So what is this? Current is actually 10 ampere, it is already given. Okay, so VL is 2 not 5, we have already obtained. I'll just erase this figure so that I get some space over here. Omega is given as, see, omega means 2 pi f. Frequency is given as 50 hertz, so we can get 100 pi here, 100 pi. So 100 pi into I is again 10. So this is in Henry unit. Okay, so this would actually give you, see, let us just do this problem like calculation. Okay, so again pi is there. If you just do the calculation, you must be getting 0.065 Henry. Okay, this you should get if you just do this simplification. Okay, you must be getting this one, and hence option D will be the correct answer. So what I have done from the initial informations, that is the direct current which is required and voltage required for the arc lamp, from there actually we know the voltage across the resistor and current through the circuit, we know, because this is the requirement. So we can write actually V square, total voltage across the, like across all the components of the circuit. V square is equal to VR square plus VL square. So from there we can obtain that VL is equal to, VL must be 205 volt, and we know VL means impedance, inductive impedance, that is XL into I. Okay, I is the current in the circuit. Now omega L into I, that is equal to VL. VL we know 205, and omega we know 2 pi into frequency 50 hertz over here. So that is what I have just put in, and then if you do the calculation, you'll get this. Okay, so the option D will be the correct answer for this question. Okay, we'll move on to the next question. The next question is that for an LCR circuit driven with voltage amplitude Vm and frequency omega is equal to omega 0, this is the resonance frequency for an LCR circuit, 1 by root over L into C, exhibits resonance. The quality factor Q. So you know quality factor, the sharpness of resonance quality factors are there in this in the resonance curve. So quality factor is defined as Q is equal to 1 by R into 1 by root over LC. Okay, this is how, I'm sorry, this is not the definition, this is root over L by C. This into root over L by C. This is the definition of quality factor. Okay. Now we know resonance frequency is given by 1 by root over LC. This is given already. So this is the definition, this you must be knowing. because deriving expression for this is not very uh, trivial or very easy. You have to spend a lot of time if you don't remember the formula. In fact, you should remember the whole, this q is equal to the whole expression itself. Okay, so now omega 0 is given 1 by root over LC. So look, if I just multiply omega 0 in the numerator of both sides, then I'll be able to get this L by root over L by C is equal to omega 0 L. So this factor is becoming omega 0 into L. Therefore, Q will be, quality factor will be omega 0 into L by R. So this is the answer. Omega 0 R by, sorry, omega 0 L by R. The option B will be the correct answer for this question. Now we'll move on to the next question again. This is a nice question over here. Let me just get on page in between. Okay, excuse me. Okay, so if you can read, you can just see in an AC circuit, the instantaneous EMF and currents are given. See, instantaneous EMF is given as E is equal to 100 sine 30 into T. So E is equal to sine omega T in that format. And this is E0, you can say. This is the amplitude. This is the frequency 30. This is 30 into T. Okay. Similarly, for RMS current, instantaneous or RMS current is given as I is equal to 20 sine 30t. Sorry, this is actually, this will be, this is not true. This is actually pi by 4. Okay, this is pi by 4. This is phase vector pi by 4. It is given like this. So in an AC circuit, that instantaneous EMF and currents are given by these two equations as you see in this here. And in one cycle of AC, the average power consumed by the circuit and wattless current are respectively. So in one full cycle, what will be the average power consumed by the circuit and what is the wattless current in the circuit? So that you have to find out. See, the average power is written as ERMS, VRMS, ERMS, VRMS into cos of phi. Okay, ERMS, VRMS into cos of phi. What is this phi? What is this phi? Phi is the phase angle between the EMF and the current. Here the phi is actually pi by 4. That means 45 degree. Okay. I can write this as peak value by root 2 and also this is IRMS. ERMS means VRMS and this is I0 peak value by root 2. That would give you RMS value. So that's how this is cos pi by 4. Okay, so see here E0 is this one E0 and I0 is this particular number. So you can write 100 into 20 by root 2 will give you 2. So this will be this. And cos of pi by 4. This is cos of pi by 4. Cos means cosine. Okay. So 10 to the power 3 cosine pi by 4 means 1 by root 2. So this is the average power. You see, I have got the answer partially. Now we have to find out wattless current. So wattless current Wattless current, expression for wattless current is wattless current is given by wattless current is given by I phi, let us write as I sine of phi. Okay, this is the wattless current. So what is the I, this is I0. Sorry, this is IRMS. I'm sorry, this is IRMS. IRMS into sin phi. IRMS can be written as peak value by root 2, and sin phi means sin, again sin pi by 4. Pi by 4 would give you 1 by root 2. So this is root 20 by root 2 into 1 by root 2. This will give you 2. Finally, it will be 10 ampere. Okay. Wattless current will be 10 ampere. So look here, in ampere, this is 10 ampere and average power is this one. So the option C will be the correct answer. I hope you understand this. Okay, it is very straightforward and you can do it. Now we'll move on to the last problem for today's session. So this problem here, you can see in the circuit shown, the switch S1 is closed. S1 is this, which is connecting the battery. This is a DC battery, you can see that DC battery with R and L. So when you close this battery, so here current will flow, and as usual, the current will be dissipated through this R. Power will be dissipated through this R alone. Okay, or this can be acting as a charging circuit if it is an instantaneous phenomena. Okay, and S2 kept open. At some later time t0, the switch S1 is open and S2 is closed. The behavior of the current I, as shown in the figure, as time. So as I said, when you charge it, it will actually uh, it will actually passes through, current will pass through when S1 is closed and this is open. Current will pass through this LR circuit, series LR circuit, and as soon as you close it, the current will actually decay. Okay, close this and you just open, sorry, you open this and close this one. That means here there is no battery, so the current which was flowing through this LR will be decaying through this okay. So that decay, see here t, okay, t starts from 0 in the graphs. So the behavior of the current you have to see. So when you start with t is equal to 0, it starts charging, okay, or current will increase, and since it is an LR circuit, the current will increase as an exponential function, okay, as an exponential function, and when it decay also will be an exponential function. So you can see which among these four is showing both exponential nature. See this, anyway this is not exponential nature, these are linear. So this is linear, but this is exponential, this is half of the thing. Here also this is exponential, but this is not exponential. But in this case, you look, both are, so increasing current is also exponential and decreasing current also having nature of exponential nature. Therefore this fourth option will be the correct answer for this question. I'll repeat the answer. Since the current is increasing in the circuit exponentially, and as soon as you open this and close this and try to measure the current or see the nature of the current will actually decrease exponentially. So both side it will be exponential, like this and like this. So this fourth option will be the correct answer for this question. Okay, so thus we'll conclude today's session. In the next class, we will take a much more problems on this is alternating currents, and we'll pick up few problems which are actually in combination with alternating current and induction part also. Okay, so thank you for your patience. Bye for today.